Okay, so this will be the final recorded lecture for Tools of Operations Research in this summer term. The last thing I wanted to talk about is just the final exam, what to expect on it, what it will cover, and sort of how it will work. So you've taken the midterm exam. The midterm exam covered the first couple topics we covered in lectures, which were data mining. Okay, so we talked about k-nearest neighbors, we talked about multiple linear regression, and we talked about one other data mining algorithm. Okay, classification and regression trees. I want to make sure I say it right. So CART, or classification regression trees. So 3 data mining algorithms. There are other data mining algorithms, but you don't need to know anything about them for the purpose of the final exam. Okay. There most certainly will be some questions about data mining on the final exam. The main thing I would suggest you think about or remember for the final exam, study about, first, the idea of partitioning and why we partition. Okay, so if you remember back, we take the data that we're doing data mining on and we partition it into 2 different subsets. One of which we use to train or build the model, the data mining algorithm, and one we use to validate the model with. Okay, the key is, the reason we do that, or the key reason why we have partitioning, is to avoid a problem called overfitting. Data mining essentially is trying to find a pattern in the data so that you can classify or predict new records or new data in the future. Okay, so it's trying to find a pattern that says some sub-portion of the data fields are important in influencing or affecting other fields. That is, if you're talking about, let's say, student data, if I wanted to predict whether or not students are going to graduate, so I might look at student data for the last several years, and I would have information like their GPA. I would have information like their, country of origin or their address, where they came from, in-state, out-of-state, whatever. I might have information about their gender, male and female, and so forth, and then whether or not they graduated. So the key of data mining is there a pattern in that data to suggest who graduates and who doesn't? That is it more likely that females graduate versus males, or vice versa? Is it more likely that people who come here from out of state versus in-state graduate or don't? Is there a combination of fields? That is, the out-of-state females are very likely to graduate, the in-state males are very unlikely to graduate, or vice versa, or whatever. So data mining is about finding those kinds of patterns. The problem is you don't know whether or not the pattern you're finding in the data is a true pattern for all data, or if it's just a nuance or a noise factor inside the data you have. So with the given data you have, there might be something that looks like a pattern that's just random luck that data exhibits that pattern, right? That it's not a true pattern in the real world. That's a problem of overfitting, finding a pattern that's not truly supposed to be there, or trying to fit a pattern that maybe is just based on random noise or random fluctuations in the data. The way partitioning avoids, or the way partitioning really helps us identify overfitting, is by building the model with one subset of the data. We can measure how well that pattern, that algorithm of data mining, works on a different set of data, the validation set. And what you'll see in overfitting is the better and better pattern you find, you'll start finding a pattern in the training data, and that's a good pattern that helps you predict the validation data. But at some point, you start finding a pattern in the training data that isn't really there or doesn't really apply in the validation data. And so you'll get a pattern that helps you do better and better in the training data, get better and better predictions in the training data, but worse predictions in validation data. Once that starts happening, you're starting to overfit. You're starting to identify a pattern that doesn't really exist overall, and you can stop the algorithm. You can basically stop trying to find the pattern and stop where you're at. And in that way, you've avoided overfitting. Okay, so validation data, training data, partitioning is how we avoid overfitting. The final exam will have something that covers that. Okay, so it's important to understand what partitioning is, what overfitting is, and how they relate to one another. It's also important to understand the metrics that we use to compare data mining algorithms. So data mining algorithms that are predicting values have, predicting numeric values, have the nice case that they are predicting a number that you can measure how close that number is to the real result. And you can have an error, you know, how off was it? And you can take the average error or the average squared error or any number of things and use that as a measurement of the algorithm, and then compare that algorithm's error rate to another algorithm. So in that way we can compare two algorithms, which one does better on a given data problem by how much error each one has. In the case of classification, where you're just picking a class or a category to put each record into, you're either right or you're wrong. So there's error, but there's not a percent error or anything like that. You're just right or wrong. And in that case, you can use things like lift charts that we've seen to visually depict how well one algorithm is doing over average or over just sort of a random guess. And then you can compare two lift charts of two different algorithms to visually see which one is doing better over the other. That is, which one has a better lift, a higher percent of records that it's doing better on than the other algorithm. Okay, so the final exam will cover something like that. Usually what I do is I show you multiple lift charts and ask you which algorithm is better and why. So you would basically look at the lift charts and be able to visually tell which one is better and explain to me why it's better. That is, from the lift chart, what makes one better over the other. The higher value in the lift chart, or the sharper the increase of the line, or whatever it is. Okay. So there'll be something like that. So data mining, that's kind of what to expect on the final exam, similar to what you saw on the midterm. Forecasting, short-term forecasting as we did it. So there were 4 algorithms we covered: moving average model, exponential smoothing, and then exponential smoothing with trends, and exponential smoothing with cycles. Okay. I will not expect you to do any kind of forecasting, large-scale forecasting. I mean, I'm not going to expect you to compute dozens of values on the final exam. It's not worth the time spent to do so. What I might ask you is to compare the output of 2 different forecasts. Okay, so something like figuring out what the error is, similar to how you did on the midterm. So I think I had you compute out of 3 forecasts what the average error was, or the mean squared error, or whatever error rate was, and then I might have you do that for 2 different forecasting models, and then compare which one's better, which one has the lower error. Again, nothing with complex math. Any math I have you do will hopefully be easy enough you could do it in your head or on pen and paper fast enough. You're more than welcome to have a calculator. Sometimes that's just quicker and easier anyway, but nothing with extensive or exhaustive math that you would have to do for forecasting. So from there we talked about optimization. So we started with linear optimization, and we started doing it by hand, where there were 2 decision variables that you can choose values for, and we both graphically depicted linear optimization problems. So we graphed the 2 different decision variables. We graphed the constraints, which said here's a value that the combination of decision variables can't be less than this or can't be greater than this. And so those constraints graphed on this 2D plane of the decision variables basically would graphically depict to us some restriction of the solution space, the possible solution space for decision variables. And so we would know sort of the range of values of the decisions that we can make. And then from there, we knew that an optimal solution for a linear problem always occurs on the edge. That is, always occurs at the corner points of that solution space restriction. And so then you just had to find where the intersection of each two constraints were, or the various constraints that would graphically create the box or the triangle or the shape that we depict, and compute where those corner points are, and then compute the objective at each of those corner points, and compute which, or tell which objective was the best, maximum, minimum, whatever. There certainly will be something on the final exam related to linear optimization. Okay, I don't. If I have you do an entire linear optimization problem by hand, it will be simple. It'll certainly be 2 decision variables, but it'll be a small number of constraints, and so no complex shapes or weird things like that. Something that you can hopefully do within about 10-15 minutes, okay? Because the final exam is time restricted, obviously. So it'll have to be something that everybody can pretty easily do within a short amount of time. From there, in the class, we talked about more complex linear optimizations using Analytic Solver platform in Excel. We talked about special classes of linear optimization, like network optimizations, which I believe was a recorded lecture only, but involved something like you would visually depict, say, in a network, the source nodes where things came from, and then maybe this represents a shipment problem where you're shipping from factories to a warehouse or two, and basically what we have to compute is each warehouse has some requirement, okay, and each factory has some capacity. So we need to figure out, of this factory's capacity, how much does it send to one warehouse versus another, and so forth, to meet the requirements here. So every factory can only send what it has in capacity, and it needs to send whatever is optimal to the warehouses such that they each meet their requirement, but that we minimize the costs associated with these shipment lines. So it might be cheap to send from one factory to this warehouse, but very expensive to ship from this factory to this warehouse, and vice versa for some of these others. So basically optimizing how much we ship on each possible route to minimize costs. The nice thing about these network optimization problems is the way we can graphically depict them. Okay, so the final exam will likely include a network optimization problem described, where I will probably provide you the optimal solution, and you will graphically depict it for me. So you will graphically show me which lines have something flowing on them and how much. So you might label the lines with like how much product goes from factory 1 to warehouse 1, how much product goes from factory 3 to warehouse 2, and so forth. Other types of linear optimization problems we covered included integer optimization, where the decision variables had to be integers or whole numbers, and a special class of those called binary optimization, where the decision variables had to be 0 or 1, which are useful for things like when we were selecting what projects to do. So there were a couple different assignments and problems we did in class that involved you have a set of projects that are possible. You want to select which ones to do and which ones not to do based on some perceived value or benefit in doing them. And obviously you have some budget or other restrictions that say you can't do all of them. So you have to pick and choose, and you can either do it or not do it. So it's a binary decision. You're either in or out. So there might be, or very well could be, a good question on the final exam about that kind of problem. Again, you won't have to solve the optimal solution. I might describe a problem and give you sort of the Excel optimal solution and expect you to read it back to me or describe it to me in terms of why it decided to do what it did, or which constraint is binding, okay, and so forth. When it comes to optimization problems and binding constraints, I think there might be a little bit of confusion that some of you have. So a binding constraint is one that prevents you from finding or selecting a better optimal solution. More often than not, binding constraints are when you have some computed value equal to a minimum or maximum, the capacity or the requirement or whatever it is. There are cases when you have a constraint that is binding, but the two parts of the equation are not equal to one another, especially when you get into things like integer or binary optimization. So thinking back to the binary optimization problem we did, I think, in class, and a similar one on the homework, where you're selecting which projects to do, you might have a budget for how much money you can spend on which projects you fund, and that budget might be constraining even though the amount you spend isn't equal to the budget. The problem is there's no other project you can select that doesn't put you over budget, right? And because you have to do the project in full or not at all, you can't just pay part of the costs. You would have to pay all of them. So the budget might still be constraining even though you're not spending it all, because there's no way you could spend more than that. There's no way you could still spend less than the budget and select another project, get a better answer, right? So any other decision you make would force you to go over the budget, which means it's constraining. So a binding constraint isn't always one where there's an equal amount on the left-hand and right-hand side of some equation. It's just one where that constraint prevents you from doing any better, getting a better optimal answer. Okay. All right. So that all being said, so there'll be some question about constraints, binding constraints or non-binding constraints. More than likely, that will come in the form of a problem that I give you the optimal answer to, and then ask you which of the constraints were binding. So I might give you a project selection problem, and then tell you here's the optimal set of projects to do, and then ask you which of these couple constraints was the binding constraint. And you would have to look and say, why couldn't I have selected one more project or done one more thing different? Is it because I couldn't spend more money? Is it because of something else? Okay. All right. That's optimization. The last thing we talked about with optimization is nonlinear optimization. I will ask some kind of question related to the difference between linear, nonlinear, and even non-smooth optimization. Okay, so linear optimization, we are guaranteed to find the best optimal answer, the globally optimal answer, but we are the most restricted in the kinds of equations we can use. We can only use linear equations. So the objective, the constraints, all have to be a linear function of the decision variables. In a nonlinear optimization, we can use more functions. We can use things like squares or square roots or logarithms, things like that. The trade-off is that we're not guaranteed to find a globally optimal solution. We are fortunate that we will always find a locally optimal solution. That is one for which no other similar solution is better. But it's possible that there exists a very different solution somewhere that has a better optimal, or a better optimum. Okay, so that's the trade-off between linear and nonlinear. Non-smooth optimization, which we talked about but did not do an example of or a homework assignment on, involves less restrictions on the number, on what equations you can use. So you can use equations that are non-smooth, things where if you graphed the equation, it's not even a smooth line anymore. It might have jagged edges, or it might have breaks where the value suddenly changes from one thing to another. And the trade-off with that being more expressive, allowing more representation of equations, is we can't guarantee to even find locally optimal solutions. Okay, so the algorithm which implements non-smooth optimization can only find, can only do its best to find a good answer. It will never guarantee to find the best answer or even a close to best answer. It'll just do the best it can and give you whatever it gets. Okay. More often than not, it'll give you a very good answer. Okay. So more often than not, unless it's an extremely complex problem, it'll give you an answer which is probably an optimal answer. But that's the trade-off of it being more expressive, less guarantees of what it will find. And then finally, we talked about tonight simulation. So simulation is about handling uncertainty. It's about when we don't know values for some of the parameters to the model, but we know, for example, that a randomly distributed function to represent them, so a range of values or a likely value within some range and so forth. There will certainly be some kind of question about the different random distributions we talked about: uniform, triangle, normal, Bernoulli, and there will probably be some kind of question that will require you to read back to me on the final exam answers to questions like what's the maximum loss, or what's the percent chance that you get a certain value or better. And what I would do is I would probably take a screenshot of Excel of the screen you see, where you have sort of the output distribution graphed and sort of the table of numbers that give you the minimum and maximum and mean and other things. And I'd expect you to read off of that screenshot to answer those questions. So something like, what's the percent chance that we lose money, and have a negative profit? And you would have to look at the right part of that screenshot and give me the right answer. Okay. So that would be how I would cover simulation. The final exam generally will be a combination of conceptual questions, things like why do we partition data for data mining? Why what kind of uncertainty do we handle with simulation? So the uncertainty of different model parameters and what value they could take on. Or why do we have simulation, at all? Well, it's to handle uncertainty, things like that. So conceptual questions like that, as well as practical questions about sort of reading off of, say, a simulation result, certain answers to specific questions, or from an optimization problem that I've solved for you, answering off, which constraint is binding, something like that. So there are practical questions, conceptual questions. There'll be a mix of the two. There won't be any particular weight or anything given to any one topic over the other. So there will be roughly the same amount of questions over data mining as there are about forecasting, as there are about optimization, as there are about simulation. Okay, so if we covered it, there'll be some kind of question related to it. It won't be heavily weighted. The final exam won't be heavily weighted toward recent material over past material. Okay, it's comprehensive in every way, and will roughly cover things. If we spent an hour talking about it in class, versus another topic that we spent 3 classes talking about, then I might ask more questions about the 3-class period discussion than I would the 1-hour discussion. But certainly I would try to ask about everything, okay, in one flavor or one form or another, through some conceptual question or a practical question. Okay, So that's all I have as far as setting expectations or explaining what will be on the final exam. Are there any questions about it? The final exam is scheduled for the full class period next week, so 3.5 hours, okay, 6 to 9:30. I certainly do not intend to write a final exam that takes everybody close to that amount of time to complete. It will be comprehensive, so certainly it'll take you more than an hour, I suspect. I try to at least write it such that it's, if you know the material, you can complete it in an hour and a half or 2 hours. Okay, if there's things you're uncertain about, or if you're not really certain, or you don't really understand fully some of the material, it might take you a little bit longer. I never intend to write trick questions in the sense that there's an obvious answer that's wrong that you have to try to overcome or resist. I don't try to write those kinds of questions. Okay? If something seems like a trick question, like there's an obvious answer that probably isn't right, then just ask me about it. More often than not, if there's an obvious answer, that's what I'm going for. I want the obvious answers. I want a straightforward answer. I try to ask straightforward questions. Most of the conceptual questions, for example, if I'm asking about why we partition data for data mining, I'm basically looking for you to explain to me what overfitting is and how partitioning prevents or helps overcome overfitting. Okay, if you have a long answer but never say anything about overfitting, or never say anything about finding patterns that aren't there, then obviously I have to question whether or not you understand. But certainly if you just say partitioning overcomes overfitting, which is finding a pattern that doesn't really exist in the data at large, and we do that with partitioning by building a model on a subset of the data and validating that the pattern it's finding, that whatever it's doing, the prediction or classification it does, is still accurate on a different set of data. That's all I'm looking at. Okay. Any other questions? No? Okay. Well, I will see you all next week, 6 p.m. The final exam will be pencil and paper, like the midterm was, so just bring something to write with. I'll have extra sheets of paper should you need them for any reason, but the final exam will have space to write on and everything, like the midterm was. If you want to bring a calculator, feel free, in case you want to check your math on some of the problems that might involve a little bit of math. I try not to take off points for bad math, or I try not to take off very many points anyway for bad math. If you made a simple mistake and off by 1, but everything else you did is correct, then I'll take off just a minor little part of the credit. So don't worry too much about doing perfect math as much as studying to make sure you understand the concepts, and so forth. All right. I will see you all next week. Good luck. And don't forget, you have assignment 7 covering simulation, and that will be due next week following the final. So like always, 11:59 on Tuesday nights.